Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Welcome back to our class EET 426 Power Electronics 2, and this is the second topic for the second part of the lecture, which is the flyback converter. Okay, this is the outline for this topic. First of all, we will cover the buck boost converter. We will review back because the flyback converter concept is based on the buck boost converter. Okay, and then we will explain a little bit detail about the flyback converter, and then we will look at the difference between the transformer model of the flyback converter versus the forward converter. Then we continue with the flyback converter detail analysis. We will come up with all the equation, and then we look at the flyback converter application, and then we will see the RCD clamp. So this is the additional circuit that we need to add to the flyback converter to avoid certain problem in the flyback converter. And then finally we look at the parasitic effect in the flyback converter. Okay, this is the voltage transfer function for buck boost converter. We have two parts here. The first one, the top here, this is when the duty cycle is less than 0.5. We have the output voltage less than the input voltage. Okay, so the converter is operated in buck mode. Okay, but for the duty cycle more than 0.5, we can have the output voltage bigger than the input voltage. Okay, so in this one is in boost mode. Okay, so we have the bigger magnitude at the output but reverse in polarity. So this is the step up side or boost side for this one. Okay, on top here, this is the original buck boost converter. Okay, but we want to show you how this buck boost converter can be related to the flyback converter. Okay, so imagine that we have one inductor here, okay, with a value L. So this is equivalent to having the value of 2L, I mean the double of this size, and then having them both in parallel. Okay, when you parallel these two value, you will get, okay, when the effective value from here to here, this will be L. Okay, but here you use 2L and this one is 2L. Okay, now that we have the value of 2L and 2L in parallel in the previous circuit, we can introduce an isolation between the input and the output circuit by having a transformer here. Okay, and we can introduce the transformer. The function will be the same, the energy will be transferred, but now we have a isolation between the input and the output side. Okay, so we have the isolation, but we have to properly design the transformer to get whatever value of inductance that we want for the primary and the secondary circuit. Okay, and then we can say that the flyback converter is just isolated forward converter with the isolation at this part. Okay, and then we can have the voltage polarity the same with the buck boost converter, which is reverse with the input voltage, and we can also have the output voltage which is the same with the input voltage. So how we can do that? By we can change the direction of the diode. We can change the dot of the secondary transformer by changing the way we wind the transformer, and then by having that we can have the output voltage which is the same with the input voltage. Okay, now we will look at the transformer model that we will use for the flyback converter. Okay, this one is just a review back of what we already learned even in the forward converter topic. So this is the ideal transformer. We have V1 over V2 equals to N1 over N2, and I1 over I2 equals to N2 over N1. And just to refresh back also about the dot convention, when the voltage at the dotted terminal on one winding is positive, the voltage at the dotted terminal on other winding is also positive. So what it means is, so when the voltage here at the dotted side here is positive, this one will also be positive. So if the voltage is negative here, the voltage will be negative at this side. And then another thing is, when the current enter the dotted terminal on one winding, the current leave the dotted terminal on the other winding. So in this case, when the current is entering from this dot at the secondary port, the current will go out from that dot here. Okay, imagine if we change the dot at this point. Okay, when the current enter from here, when the current enter from this side, this one is positive, so the current will leave from this side. Okay, this is the detailed model or the real model of the transformer. We have the R1 and R2 here represent the resistance of the conductors. You know that the winding of the transformer, okay, the primary and secondary winding, the winding itself have some resistance, so the resistance there is represented by this R1 and R2. And then we have the L1 and L2 represent the leakage inductance of the winding. So this is the to represent the flux that have been leaked or not connected to the secondary winding. Okay, and then we have the LM that represent the magnetizing inductance. So it is linked to the flux that actually being linked to the secondary winding through the core. And then the RM is represent the core loss. Okay, the losses due to the core of the transformer. Okay, for this chapter, for the flyback converter, we will only take into consideration of the magnetizing inductance, and we will ignore all other the real transformer parameters such as the R1, R2, the leakage inductance, and the core resistance. Okay, so for the operation side, we will see the flow of the current, and we'll take into consideration the impact of the magnetizing inductance of the transformer. Okay, now we will look at the hysteresis curve of the transformer. Okay, and in this you can see in the red area here, this is the magnetic system energy input. The energy occurs in the transformer. Okay, and then at this portion, the blue portion here, this is the energy stored in the transformer. And finally the green area here, this is the hysteresis loss occur in the transformer. The hysteresis loss happen due to the reversal of the magnetization in the transformer core. Okay, this is the ideal magnetic core hysteresis curve. So in this you can see that there is no energy storage here, and then for this the value of inductance is infinite. Okay, this is the hysteresis curve for the real magnetic core. In this we have a finite value of inductance, and for high value of inductance you can have low energy storage, but we can have high energy loss in terms of hysteresis loss. Okay, this is the hysteresis curve when we consider the real magnetic core, and then for this we have the reduced inductance value. So from the infinite become the finite value, but we can increase the energy storage. Okay, we have some energy storage, but it consider small. Okay, and this is the hysteresis curve when we have the air gap core. So the air gap is when you have the core and then separated by air gap. So what happen is you have the reduced value of inductance, and this impact this curve here. Then here we can see that we have huge energy storage here, but reduce energy loss. Okay, now we look at the isolated forward converter and flyback converter transformers. We want to compare both of them. So here we have the forward converter transformer. Usually it will use the gapless core structure. Okay, with the solid one without any air gap. So it will perform as a normal transformer, transferring energy, and you can see here very small energy storage here is in terms of the leakage inductance represent energy stored in the non-magnetic regions. Okay, for the flyback converter, okay, the transformer is basically a coupled inductor. Okay, we already explained in the earlier part of this lecture that the inductor from the buck boost converter, we can make it into two component, primary and secondary part of the transformer. And then for that they use the air gap core. So this flyback converter is designed with air gap core for the purpose of having as energy stored, okay, energy storage here. So the primary side will store the energy when during the switch on time, and this energy will be released to the secondary circuit or to the load during the switch off time. So basically the flyback transformer is just a two winding inductor, okay, separated by, okay, in terms of transformer primary and secondary, and energy is stored in the magnetizing inductance here. Okay, so the current does not flow simultaneously in primary and secondary. So during the turn on time, the current is stored, the current flow here, and the energy is stored here. And then when the switch is off, this energy inside of this inductor will be transferred to the secondary side. Okay, remember in the forward converter you have the demagnetization pathway. Okay, but for the flyback converter there is no requirement for demagnetization. Okay, because the energy that is stored uh, in the transformer primary winding or in the magnetizing inductance will be transferred to the secondary during the switch off time or during the rectifier on time. Okay, when the switch is off, the rectifier in the secondary will be forward bias. That's why we mean in here the statement is rectifier on time. Okay, in short, the flyback and isolated forward converter transformers differ in the following area. The first one is the function of the transformer. Second one is the structure of the transformer, the type of core that it used. And then the third one, the requirement for the demagnetization of the transformer core. And then finally, the effect of leakage inductance, okay, to both transformers. So they will differ in these four areas. After this, we will look at each one of them. In the first difference is the function of the transformer. For the flyback converter, this is just a coupled inductor, okay, that stores primary side energy during the switch on time, and this energy will release or will be released to the load during the rectifier on time, or in other words during the switch off time. Hence the primary function is to store energy, not to simply transfer it. Okay, but it's differ from the isolated forward converter. So in isolated forward converter, when we have the switch on time, okay, when we supply the transformer winding, the primary winding, the energy is straight away being transferred to the secondary winding, okay, without the need for energy storage. Okay, to achieve different function for transformer that we just mentioned, the design of the transformer itself have to be different. Okay, for flyback converter, because we need to store the energy, so we have to design the core of the transformer to be to have the air gap, and this is required in series with the high permeability magnetic core material that we must use in the flyback transformer. And for the isolated forward converter transformer, so the transformer itself don't have to store the energy, so it will use the gapless core structure, so that there will be a little energy storage in the transformer. Okay, the next one is the demagnetization requirement. If you remember from the previous topic regarding the isolated forward converter, the converter required a reset winding. Okay, because without the reset winding, there will be a core saturation, and this will increase the magnetizing current the next time the transformer turn on. Okay, but because of the flyback converter, it store energy during the switch on time, and the energy is transferred to the secondary during the switch off time or during the rectifier on time. There is no requirement for demagnetization, okay, because the energy can be stored and then released during the switch off time. And finally, the difference between both type of transformer is the effect of leakage inductance. In isolated forward converter, the leakage inductance will result in the reduced output voltage due to the voltage drop and due to the overlap. But the leakage inductance will impact the flyback converter by causing the high voltage spike, and this can lead to the MOSFET avalanche breakdown, which is the total breakdown, and this will cause damage to the MOSFET. Okay, and to avoid this, we need to have additional clamping circuit. Okay, that's all the lecture for this part. After this, we will continue on the flyback converter analysis, where we will look at the equation of the flyback converter, how we can derive the equation for flyback converter. Okay, so that one will be in other video. So thank you for your attention for this session, and I hope you can take some knowledge from this video. And if you have any question, you can contact me directly, so we will discuss if you have any problem to understand any part of this video. So thank you. Assalamualaikum warahmatullahi wabarakatuh.